harmonic conjugate of a real value function is still the basis of what we've done so far, or is still the basis of the third example. For the third example, or for the last example we had, he said you'll be given the partial derivative, right? Given that partial derivative, the question says that find the what? Analytic function. Find the analytic function. But in this case, you'll be given real value function. From this analytic function, I have real value function, meaning I have real part. By complex number, we have what? Real number and imaginary number. So by the word real value function, we are saying that you'll be given a real value function, then find the imaginary function. But the idea here is that I want to find the harmonic conjugate of a real function. Before you can find the harmonic conjugate of a real function, the function you are finding the conjugate, it must be an harmonic function. So how do you test? Given a function, how do you test if this function is an harmonic function? Are you getting me? I already have the understanding now that question says that find the harmonic conjugate of a real value function. And I'm saying that before question can tell you that you should find the harmonic conjugate of a real value function, that function itself must be an harmonic function. The question now is, given a question, before start solving anything I know about harmonic conjugate, how do I even identify that this question given to me is an harmonic function? Is what? Is an harmonic function. Meaning that that function must satisfy the two-dimensional Laplace equation. The function must what? Satisfy the two-dimensional Laplace equation. When we are saying two-dimension, meaning the x-axis and the y-axis. When we are saying three-dimension, we are saying the x, the y, the z. How do you represent it? You are saying the partial derivative of u with respect to x plus the partial derivative of u with respect to what? Y plus the partial derivative of u with respect to z. Right? So now I'm saying that the function must satisfy the two-dimensional Laplace equation. You see the same thing? Meaning in this case, two-dimension, I'm referring to the x-axis and to the what? Y-axis. Meaning that the partial derivative of u with respect to x plus the partial derivative of u with respect to y. But in this case, just note that before your function, a function is said to be an harmonic function. Are you with me? A function is said to be an harmonic function if this equation is met. If this two-dimensional Laplace equation is met or is satisfied. So whenever you see this is Laplace equation. This is the square u So from what I said you are given a function, you want to find the conjugate. Okay, let me bring it back to what we know. Say you are given a complex number, say z is equals to a plus jb, call this one, and z is equals to a plus b, call this 2. Now my question is that find the conjugate, find the complex conjugate of one. Okay, let me use value. Say this is 3, say this is 4, and say this is 2, and say this is 4 also. Now 1 and 2, my question is that find the complex conjugate of this function, meaning find the complex conjugate of equation 1 and find the complex conjugate of equation 2. What's the answer to 1? If you still remember what conjugate of a complex number is saying, by the word conjugate, if I'm having plus, the conjugate becomes what? Minus. If I'm having minus, the conjugate becomes what? Plus. Now my question is, find the conjugate, find the complex conjugate of equation 1 and equation 2. What's the answer to equation 1? What's your answer to equation 1? Meaning the conjugate, which is z bar, is equals to 3 minus j4. Correct. Number 2, find the complex conjugate of equation 2. What's the answer? First thing first, is it a complex function? No. It is not. So how come question says that you find the complex conjugate? It is not possible. Even though you find the conjugate, we are wrong, or we are already doing another thing. So I'm not saying that harmonic conjugate of a real value function. You want to find the conjugate of a function. First thing first, that function must be an harmonic function. Once you've identified that this function is an harmonic function, of course you'll be able to find the conjugate. That's it. Alright, I'm not giving this question, I'm giving this function. Then the question I'll ask myself is that how do I identify, or how do I know if this function is an harmonic function? This condition must be met. And this is what we call the two-dimensional Laplace equation. What did I say? Two-dimensional Laplace equation. Meaning, once your two-dimensional Laplace equation is met, given a real value function, then that function is an harmonic function. So this is the first thing we need to know. This is the first thing we need to know. Now, from here, we've written this down, right? Now, from here, let me just explain the whole idea of harmonic function or harmonic conjugate. By the word harmonic conjugate, you'll be given a real function. All the harmonic we've been saying, we are referencing it to real value function, right? When we made mention of harmonic, or when we said harmonic, let's say you have f of z is equals to u all into bracket s comma y plus j all into bracket. For that third example, we are told to find the f of z, meaning the analytic function. By analytic function, it means that by the time you apply Cauchy-Riemann's equation, that function satisfies Cauchy-Riemann's equation. I get what I'm saying. What we did previously, we found the when we got the f of z, meaning the analytic function, it means that by the time you apply the condition of Cauchy-Riemann's equation, it means that function is analytic. It is analytic just because Cauchy-Riemann's equation is satisfied for that particular function. Now, by the word harmonic conjugate, we are saying that you'll be given the function of u. You'll be given what? The function of u. The question now says that find the function of v. Find the what? Function of v. Now, I'll bring it back to what we've done so far. Our first example was that f of z is equals to s squared minus y squared plus jv all into bracket 2xy, right? This was our first example. Then by the time we implemented Cauchy-Riemann's equation, we saw that this function is analytic, right? We've seen that already. Now, to explain what this guy is saying, it is saying that imagine that you are giving u as a function of s squared minus y squared. Say you have this. Now, let's say you are giving v as a function of 2xy. Say this is 1. Let's say you are giving v as a function of 4y squared. Say this is 2. From this is what I was giving. This is the given question. From this given question, let me now say that I'm having f of z is equals to x squared minus y squared plus jv all into bracket 2xy. And I'm also having f of z is equals to s squared minus y squared plus jv all into bracket 4y squared. Right? These two guys, they are analytic function, right? By analytic function, is Cauchy-Riemann's condition met for these two equations? Now, based on what we've done so far, which one do you think is going to satisfy Cauchy-Riemann's equation? The first one. It is the first one because you already know that the first example we did, it satisfied Cauchy-Riemann's equation. Now say that you've not done the example. How do you know that it satisfies Cauchy-Riemann's equation? What do you say? Says, okay, let me add x. If that's it. Are you getting out of? Now from here, I was giving this, right? Are you getting me? The question giving, say I'm giving a question. I was giving this function, which is the real value function. I'm now saying that, before you can have an analytic function, you are having u function and you are having v function, right? Now say we found these two v function, or we know these two v function. I want to write my analytic function, which is f of z. I'll be having these two, right? Me having these two, one of these two analytic function is correct. It is correct because one of them, the Cauchy-Riemann equation is met. It is met. But the question is, how do I know the one that is correct? How do I know the one that is correct? Let's say this is 1. Let's say this is 2. By the time I apply Cauchy-Riemann equation to this, will Cauchy-Riemann equation be satisfied? Do we know? No. For this one, will Cauchy-Riemann equation be satisfied? You don't know. How do you know? You have to test it. But based on the example we've done so far, or based on the first example we had, which one will satisfy Cauchy-Riemann equation? The first one. So what harmonic conjugate of a real value function is saying that find the corresponding value of v that will satisfy Cauchy-Riemann's equation for the u function given. What did I say? Find the corresponding value of v that will satisfy the Cauchy-Riemann's equation for the u value given. You know, this is correct. This is actually correct. Why this is not correct? If you have to do it now, saying we are using partial du over partial dx is equals to partial what? Dv over dy, and partial du over dy is equals to negative partial dv over dx. You are going to see that these two equations will be satisfied for this first analytic function, but not for this. You know, given the question, you are given this. How do you now know the correct v function that will satisfy Cauchy-Riemann's equation for that particular analytic function? Are you getting me? So that's what it means by harmonic conjugate of a real value function. Meaning, by the word harmonic conjugate of a real value function, you want to know the imaginary part, the correct imaginary part that will correspond with the real part of the analytic function that will satisfy Cauchy-Riemann's equation. That will what? Satisfy Cauchy-Riemann's equation. So that's it. Any question on that? Or do you need more explanation? Do you understand? So that's it. So we are saying that harmonic conjugate of a real value function, you want to know the correct function of v corresponding to u that will satisfy Cauchy-Riemann's equation. Now, we said, first thing first, given a question, your first step is to check if this equation is satisfied. Meaning that by the time you obtain these two differentials and add them together, if you are getting 0, it means that that function is an harmonic function. If the function is an harmonic function, of course, it's going to have harmonic conjugate. It is going to have what? Harmonic conjugate. Now, let's take our first example. Find the harmonic conjugate of the real value function given, or you say of the real function given. Find the harmonic conjugate of the real function given. So, right, this is the real function. By real function, you are saying that, you know, for a complex number, it has real part and imaginary part. So, the real part, meaning real function, this is it. Now, find the imaginary part, which is what? V. But we are saying that find the harmonic conjugate, not just find V. You know, he's saying finding V, you are saying another thing entirely. It is a different scenario. But find the harmonic conjugate. By harmonic conjugate, we are saying that by the time you know this your V that you are looking for, and this U given, by the time you perform Cauchy-Riemann's equation, or by the time you check the Cauchy-Riemann's equation, the first condition and the second condition, it must be met, it must be satisfied. So once these two conditions is satisfied for the V that you are finding, or the V that you are looking for, it means that becomes the conjugate of this function. If otherwise, it means that's not the conjugate. So you are saying that find the harmonic conjugate of this real value function. First thing first, given this question, before you know, from here now, any question on how to find V? Applying what we did previously, any question on how to find V? It remains the same. But before you start applying that idea, or before you start applying that understanding, check if this function is an harmonic function. If this function it is not an harmonic function, don't bother, don't stress yourself. You can just write not an harmonic function. So how do you check if it is an harmonic function? This Laplace, okay, let me write it. We said two-dimensional Laplace equation. Right? Two-dimensional Laplace equation. Now, from this two-dimensional Laplace equation, what do I need? I need the second partial derivative of u with respect to x, right? Plus the second partial derivative of u with respect to y. Meaning you are going to differentiate twice, right? You are going to what? Differentiate twice. Meaning higher derivatives, higher differentiation. Now from here, from this function, let's find these two derivatives. The first one, partial du over partial dx. What's the answer? We are doing partial derivatives. By partial derivative, for this particular partial derivative, this is your interest. I believe you know how to do partial derivatives. So just tell me your answer. Partial derivative of u with respect to x is what?
E raised to
the power of x. E raised to the power of x cos y. That's correct. E raised to the power of x cos y. Alright. Let's find the next one. The partial derivative of u with respect to y. This is what? Minus e raised to the power of x sin y. This is just the first derivatives, right? This is just the first derivatives. Now let's find the second derivative, which is, that's what we need. By second derivatives, we are saying higher derivatives, right? Alright, so let's find the second derivative, meaning partial the square u over the x square is equals to what?
E raised by x plus y.
That's what?
E raised by x plus y.
E raised to the power of x
Plus y.
cos y. The next one, partial derivative of u. The second partial derivative of u with respect to y. What's the answer?
Minus e raised by x plus y.
Minus e raised to the power of x minus e raised to the power of x plus y. Alright, from here, input values, right? The second derivatives, substitute it into the what? 2D dimensional Laplace equation, right? Now let's do that. By doing that, it becomes the Laplace, the 2D dimensional Laplace equation becomes what? Substitute value. This first one is what? This first one is what? Exponential r raised to the power of x cos y minus exponential r raised to the power of x cos y. This is equals to what? 0. Now with this, what do you have to say about this function given? It is what? It is an harmonic function. If this function is an harmonic function, it means an harmonic conjugate will exist. But if, let's say, this was not equals to 0, what does it mean? Harmonic conjugate does not exist. Meaning you don't need to start stressing yourself, implementing what you know when it comes to you finding the function of v. Alright, since we said this is an harmonic function, this is what? An harmonic function. The next step is what? Find v. The next step is what? Find v, which is what? Harmonic conjugate. How do you find v? What you just need to do for me now, go back to the way we found the first v for the last example. Our first step was what? Integrate what? You know, before you start integrating anything, you know the function, you know all the partial derivatives, right? Before you start integrating anything, you found the what? Partial derivative. You know all the partial derivatives. Now, in this case now, for meaning all the partial derivatives in Cauchy-Riemann's equation, I must know it. But out of these 4 derivatives, I already know 2, right? Now let's find the other 2. Finding the other 2, write out your equation saying that the partial derivative of u with respect to x is equals to the partial derivative of v with respect to what? Y. Then the second one, the partial derivative of u with respect to y is equals to negative partial derivative of v with respect to y. Call this 2. Okay, with respect to x, call this 2. Now from here, from this first condition, it implies that, what does it imply? It implies the partial derivative of v with respect to y is equals to what? This condition 1, this equation 1. Equation 1 implies what? Partial derivative of what? V with respect to y is equals to what?
X plus Y.
This is it here. Exponential always power of x cos y. From 2, it implies what? It implies partial derivative of v always power of what? X is equals to
E sine Y.
X and Y.
Do you know why the negative is not there again?
Yeah.
Because it has multiplied each other. I'm having negative here. Then this negative, we multiply it, it becomes what? Positive. It becomes positive. So I'm saying that out of these 4 derivatives in Cauchy-Riemann's equation, I already know all of these 4 derivatives. Now, go back to your first step in finding V, in finding the function of V. You can use any of these different derivatives. You can use the V dy, you can use the V dx. But don't forget the logic. If you are using the V dy, integrate with respect to y. Once you integrate with respect to y, differentiate with respect to x. If you are using the V dx, integrate with respect to x. Once you integrate with respect to x, differentiate with respect to y. So it is your choice. Any of these, you get the same thing. So with that, you guys will be the one telling me what to write on the board or what to do. So give me values or give me what to do. Vx comma y, v all into bracket, v as a function of x and y is equals to integral of what? Just tell me the function, the derivative first. The partial derivative of v with respect to y, right? So you are saying integrate this with respect to y. All right, now let's substitute value. What's the value of this? We are saying v all into bracket x comma y is equals to integral. This is what? What's this? What's the value? Exponential of x cos y dy. All right, now let's integrate this. Is this your usual integration?
No.
This is partial what? Integration. So by partial integration, you are integrating. No. That's what I'm saying. It is different now. I said, is this your usual integration?
No.
Okay, from what you have here. Wait, you answer that by yourself. From what you have here. Let me write this and you tell me the difference now. Let's say you are. Hello, are we together, please? Now, from this integral function, let's say you have integral exponential raised to the power of x cos x. Say this is 1, and you're having integral exponential raised to the power of y cos y. Say this is 2. Now, this initial one that I want to integrate and these other 2, what can you say about them? What's the difference? This is a function of x alone. What about this? This is a function of what? Y alone. What about this? So this is partial integration. This is the normal integration that we know. By normal integration, meaning integration by parts, right? Let's say we want to perform integration techniques to this. It becomes what? Integration by parts. From here, we are saying that this is what? This is partial what? Integration. This is what? This is partial integration. So by partial integration, factor out your what? Constant. Factor out your what? Your constant. So you factoring out your constant, you have v as a function of x comma y is equals to exponential of x integral cos y dy. Now let's integrate this. Meaning I'm having v as a function of x comma y is equals to exponential of x multiplying what? Sin y. By the time you integrate cos y, what do you have? Is it just plus c? Plus c all into bracket x. Whenever you are integrating with respect to y, meaning your constant adds x. And even you integrated with respect to x, your constant add y. But in this case, I've integrated with respect to what? Y. Meaning my constant is taking what? X. All right. From here, what do I do? So I have v all into bracket s comma y is equals to exponential always power of x sin y plus c of x. You know, this is the function. Given the real value function, which is u comma y equals to what? Exponential of x cos y, right? What was the question given? Given this question, find the conjugate, meaning v. So we found v, but I can solve for c of x, right? I can solve for what? C of x. So how do we solve for c of x? Differentiate what? Call this equation 2. So differentiate equation 2 with respect to what? With respect to what? X. So you are saying that the v over the x, the partial derivative of v with respect to x is equals to what? Differentiate this with respect to x. What do you have?
Sin y now, and y is constant.
Plus c prime of x. But the partial derivative of v with respect to x is what? Check. This is what? Are you guys are confused? Okay, don't know how we differentiate this. You want to differentiate this, take the one that has function of x, differentiate the function of x, you still have u power of x, multiplying what you are left with, you have this, plus by the time you differentiate this, you have c prime of x. So this is it. Now from here, we now said, but the partial derivative of v over x is what? What do you call it? Exponential always power of x sin y. Therefore, from this, say this is equation 3. Therefore, from equation 3, I'm having exponential raised power of x sin y is equals to exponential raised power of x sin y plus c prime of x, right? Meaning c prime of x is equals to 0. Yes. This will cancel out. So you are saying c prime of x is equals to 0. By the time you integrate both sides, meaning c of x is equals to c. C of x is equals to what? C. Back to equation 2. Your c of x, what do you substitute? C. You then substitute what? C. So up to this last value, I didn't know that c of x is c. So what do? I substitute. So I'm saying that from equation 2, v as a function of x comma y is equals to exponential always power of x sin y plus c. Sin y plus c. Therefore, given that u of x comma y is equals to exponential always power of x cos y, right? The harmonic conjugate, meaning x as a function of, meaning v as a function of x and y is equals to exponential of x sin y plus c. Writing your analytic function, meaning f of z, which is equals to u plus jv, it implies that f of z is equals to what? Exponential always power of x cos y plus j exponential always power of x sin y plus c. So this is it. So meaning by the time we check the condition for Cauchy-Riemann's equation, which is what? The partial derivative of u, with respect to x is equals to the partial derivative of v with respect to y, and what? The partial derivative of u with respect to y, and is equals to negative partial derivative of v with respect to x. By the time you test this equation for this given function, you will see that it satisfies Cauchy-Riemann's equation. It satisfies what? Cauchy-Riemann's equation. Now say that at the end we got v as v being a function of x comma y as exponential always power of x tan x plus c. By the time you substitute this, the function, will the function satisfy Cauchy-Riemann's equation? No, it will not satisfy Cauchy-Riemann's equation. So by harmonic conjugate, we want to know the correct function of v corresponding to u, which was the function given that will satisfy Cauchy-Riemann's equation. That will satisfy Cauchy-Riemann's equation. So that is what harmonic conjugate of a real value function means. And this will be done if the function given itself is an harmonic function. How do you check? Use the Laplace two-dimensional equation. Use the what? Laplace two-dimensional equation. So this is harmonic conjugate of a real value function. This is we using the partial derivative method. We also have another method which is very easy. One of the easiest methods so far. So this method is called the Mining-Thompson method. Mining-Thompson method. This is the spelling. This is the spelling. Thompson. This method that we've done so far, or what we've done so far, is look easy, right? We were able to understand what we are doing. But by the time you know this is very easy compared to this very one. This one, it helps us to know our f of z directly. You know, for this one now, we first of all find u as a function of x and v as a function of x, then substitute it back to f of z. But you see this one, it helps to know your f of z directly. F of z directly. Yeah. So for this, let's take two examples. We are going to solve the same question using this method. They are going to take another example, still using this method.